Time to get into the foundational pieces of geometry. Unfortunately, that means we need to start out by going over a lot of vocabulary. Not everyone's favorite, I know. Now, the study of geometry mostly dates back to this guy, Euclid, who wrote a series of books called Elements, which laid out a lot of the stuff that we will be doing in this course. Elements was used as a math textbook for over 2,000 years, well into the late 1800s. Think about that. That's a long time to have a textbook. This geometry stuff has been around a while. We could do all of today's vocabulary in his terms. He originally defined a point as that which has no part. I think we would significantly increase the difficulty of this course if we tried to parse ancient Greek phrasing on top of the material. A more modern definition might be something like an exact location in space. Now that's fine and all, and probably more preferable than Euclid's definition, but if I had asked you what a point was before I had said anything, you probably could have imagined, pictured, and drawn a point. It's just a point. That's all. You don't really need an official definition beyond that. What is actually a more interesting question is, how big is a point? Which one of these is correct? How big is it? Okay, this last one is a little bit ridiculous, I know. What's your guess for the right answer? A point has no size or dimension. It is infinitely small. It has no height, width, or depth. Any of these work. Go with whichever one helps you remember it best. But since a point has no size, then technically all of the points that we have drawn on this page were too big. But imagine a world where we couldn't actually draw points. Let's say I have a point here. I can't actually draw it since that would be too big, but just imagine that we have a point here. And I also have a point here. Can't draw it, that'd be too big, but it's right there. And finally I have a point over here. You got those 3 points? Great. Now let's do a problem using them. That would be ridiculous. So even though all of these points that we drew were too big, we have to draw something, so we draw a point, preferably a pretty small point. Yes, it's technically too big, but we just roll with it. Now we come to naming a point. Do you know what we use to name a point? We use a capital letter. So I can label this point with an A. And with that in place, we can now call this point A. Now we get to a line. Just like a point, you probably already know what a line is. It's just one of these. It's critical to note that I drew both ends of the line here with an arrow to make it very clear that a line goes on forever in both directions. Similar to the point, how big is a line? Which of these is correct? A line is infinitely thin. You shouldn't be able to see it. So all of these are technically too big. But just like a point, it would be pretty ridiculous to use lines you can't see. So any of these are fine, although that bottom one again is pretty crazy large. There are 2 ways that you can name a line. You can label a point with a capital letter. You can label a line with a lowercase letter. Once this line has been labeled with a lowercase a, you can call this line A. Now that works, but it is actually the less common way that you will see it. A more common way to name a line requires you to have a line with 2 of the points on that line already labeled. Here I have a line like that. With these 2 points labeled, I can call this line AB. That's much more common than the top one. However, we can actually go one step further. There's actually a symbol for a line. It looks like this. I would hate for you to get a hand cramp by writing out 4 letters, so this will save you from that. Notice that the symbol for a line also has 2 arrows on it. Without those arrows, it means something else. Most of the time, you will name a line with the bottom method and using the symbol. One last thing for a line. Do you think you can use either line AB or line BA for this line here? Both of them describe the same thing, so either is fine. Now we get to a plane. Amazingly enough, that doesn't mean this. A geometric plane is a flat 2-dimensional surface, like a floor, your computer screen, or a piece of paper. However, unlike those examples, a geometric plane, by definition, goes on forever. Planes don't have any edges. They have infinite length and width, but no depth. Imagine it like a piece of paper that goes on forever, but it is infinitely thin. Typically, a plane is drawn as a slanted figure like the one shown here. The thing to remember is that even though we have drawn it like it has edges, a plane has no edges. The slanted figure is just there to show you which plane we are talking about. Just like a line, there are 2 ways to name a plane. The first way is to label it with a capital letter, just like a point. With this plane now labeled, I can call it plane P. That's the first way to name a plane. The second way to name a plane is to use 3 or more named points that lie in the plane to name it. Here are a bunch of named points on this plane, including the corners of this slanted figure representing the plane. That's often what is done, for convenience mostly, even though a plane technically doesn't even have corners. Is that confusing? Just know that you will see it a lot, but it doesn't mean that there are actually corners there. Now with that out of the way, we have a bunch of named points. You can use any 3 or more of those points to name this plane. Any of these are possible names you could use here. Pause if you want to verify. Now we come to space. What is space? Is it the final frontier, like on Star Trek? I would say this picture is wrong, but it's actually kind of right. Look at this progression. We started with a 0D point that had no size. Then we had a one-dimensional line that went forever, hence we had 2 arrows. Next we moved on to a plane which went forever in 2 dimensions, but was infinitely thin. The pattern should be obvious. Space is the next one in the progression. So that picture of space really was right. Next we are dealing with collinear. Time for some Latin roots. The first part, co, means together or with. Then we have the linear part which pertains to a line. Put them together, and you have collinear points are points that are together in a line. Here are 3 points. To check if they are collinear, put something flat along them to see if they all line up. You don't actually have to draw in a line, but you can if you want. These 3 points are collinear. Note that before I drew in the line, these were still collinear points. As long as you could draw a line through them, they are collinear. We aren't going to trick you. If you need to, you can put something flat on the screen to verify that they really aren't collinear. But I had a student one time really struggling with a question like this about whether these were collinear or not. After much consternation, he decided to do this as his answer and declare that yes, they were collinear points. We aren't here to trick you. It should have been an easy answer of no. What do you think? Should I have given him credit for this, creative answer? Now we get to our first golden rule for the year. Any 2 points are collinear. Even with no actual line drawn between them, they are still collinear. Imagine 2 points. No matter where they are or how far apart they are, you should be able to imagine that you could have a line drawn between them. They are collinear. Here I have a blue box. Here are 2 points on the box. They don't actually have a line drawn between them, but they are still collinear. I could draw a line between them, and that's all that matters. In fact, you don't need a picture at all. Any 2 points anywhere are collinear. Coplanar is very similar. Coplanar also uses the same Latin root co, so instead of points together in line, coplanar are points together in a plane. Here is a very yellow plane. Let's mark 4 points in the plane. Since all of these points lie in the yellow plane, we can say that these 4 points are coplanar. That's all there is to it. That's how coplanar works. Another golden rule. This time, though, we know that any 3 points are definitely coplanar. We move on to line segments. Segment means piece, so a line segment is simply a piece of a line. Here is a typical line segment. Note that we don't have arrows anymore since a line segment doesn't go on forever. It stops. The points on the ends of the segment are known as endpoints. So for this line segment here, each of the points on the ends are endpoints. Now when we had a line, we had arrows on each end. It didn't stop or end in either direction, so a line doesn't have endpoints. When we had a line instead of a line segment, we named it line AB, either written out or using a symbol. For this line segment here, it is very similar. It could be written out as line segment AB, or more commonly, it uses that symbol you see there. It is just like the line symbol, except there are no arrows. That's important. You can't have arrows for that symbol. Also note that you can say it in either direction. Line segment AB is the same thing as line segment BA. Next up on the vocabulary list is array. We did a line that went forever in 2 directions. We also did a line segment which stopped in both directions. Array is what's in between those 2 things. Instead of going forever in 2 directions or stopping in both directions, array has one endpoint and then goes forever in one direction. Imagine it as a laser pointer. A laser pointer has an endpoint and then shoots out a laser that theoretically could go on forever in one direction if it was powerful enough. It's good we don't actually have a laser pointer here though, since it would bring the cats out and they would go around and chase it. And yes, that was a cameo from my cat. Here is array. If we want to be able to name the ray, you have to have both the endpoint and one other point on the ray named. Here I have the endpoint named A and one other point on the ray named B. With those in place, I can say ray AB. There's once again a symbol for array. It looks like this. Notice that there is only an arrow going in one direction. But what happens if I draw a ray like this instead? How do you think we name it now? Is it like this? Maybe it's like this. How does this one look? Some people will like this one. I will tell you now that one, and only one, of them is correct. Does orientation of the ray matter? If I had a ray like this, would I then write the ray with my arrow pointing up like it to match? What do you think we do? Any guesses? The answer is that the ray symbol always points to the right no matter what the picture looks like. The first letter is always the endpoint of the ray. The second letter is the direction the ray is going from that endpoint. Make sure you understand that. It's one of the common mistakes that students do with rays. Opposite rays are just what they sound like. They are rays that go in opposite directions. If I put some labels on them, then I can name them ray YX and ray YZ. Those are opposite rays. Note that opposite rays share a common endpoint and together form a line. You may be asked to find and name some opposite rays in the picture. If you are, then you need to find 3 collinear points. The middle point of those 3 points will be your common endpoint. Here it is point Y. Opposite rays will always start with the same letter. One of the common errors students make with naming opposite rays is they don't find 3 collinear points and then they try to do something like this. Opposite rays need a common endpoint. They cannot overlap. These are not opposite rays, but I see students do it all the time, so be careful with that. The last vocabulary word is a postulate, sometimes called an axiom. It's a statement assumed to be true without proof. We don't do a lot of assuming in geometry, but these we do. They are usually so basic and so common sense that we can just assume them and not worry about it. Here is an example of one. Through any 2 points, there is exactly one line. Since lines are straight, then of course there's only one line that connects 2 points. That's an example of something so basic, so simple, we can just assume it is true. Most of the time, a postulate will generate a well duh reaction. Do you know where that font for the well duh comes from? Any guesses? It's the Simpsons font. I figured Homer was appropriate for something so obvious. But that's the reaction most postulates will get. Well duh. Lastly, we have covered a lot of the basic vocabulary for geometry in this section, and it is one of the longest videos of the entire year. But most of the vocabulary isn't that tough. Geometry is filled with a ton of pictures. You'll have more pictures on your practice problems than probably in all of your math classes put together up till now. They are everywhere. And one of the toughest things for students, especially new geometry students, is knowing how to interpret and go beyond the picture. Here are 2 points, but you have to be able to go beyond what you see and know that these points actually have no size. Are they collinear? Yep. Even though there isn't a line drawn there, they are still collinear. That's going beyond what you see. Here I have line segment AB, but can we also talk about line AB or ray AB? Do those exist? Sure. Even though they aren't actually drawn in, we know exactly where they are and what they would look like. We can absolutely talk about them. That's going beyond the picture. Here I have plane P, which doesn't actually have any edges, even though it looks like it in the picture. You have to know that those edges are just there for practical purposes. There aren't actually any edges to the plane at all. Sticking with planes, here I have a box with one side shaded in. If I'm talking about the actual side of that box, then yes, it does have edges. But if I am talking about that side of the box as a plane, then suddenly it doesn't have edges anymore. Tricky, tricky. You have to take what you know and apply it to the picture you see. You have to be able to go beyond what is just shown in the picture, or sometimes disregard some parts of the picture, like the edges of a plane. That's the hardest part of not only this section, but for a lot of geometry for many students.